ruthenium-2 silicon-2, and so on and so forth, which possess very interesting properties. So if one measures the effective electron mass through the specific heat measurement, and you remember from your course of advanced statistical physics, and also what I said you, that specific heat is proportional to the mass of quasi-particle. In this system, this effective mass of quasi-particle is 1,000 times larger than bare mass of electron. So it was puzzling and still puzzling. So this puzzle is not resolved. Why it happened that electron becomes so heavy in this system? Another way to measure electron mass is to measure the behavior of electron in the magnetic field, so-called Brigade-Van effect, which provides a measurement of electron's orbit, an effective cross-section, which is again proportional to mass, depends on mass. This experiment also provides information that the mass of quasi-particle is extremely high. So one of the theories on the market says that these strongly correlated systems, like heavy thermals, are subject to Kondo physics. Although they are stoichiometric regular system, the Kondo scatterers sit in every side of the lattice. So unlike Kondo impurity problem, and this is a quantum impurity or Kondo impurity problem, the effective description of heavy fermion compound falls into the class of Kondo lattices. And this effect of strong enhancement of the scattering manifests itself in strong enhancement of the electron mass, which is a manifestation of effects of strong correlation. So in quantum dots, the same effect manifests itself in facilitating electron transport through the quantum dot, and therefore it can enhance conductance, namely the proportionality coefficient between current and voltage up to unitary limit, maximum value of conductance in finite size system, and therefore, if Kondo effect is controllable in such kind of single electron transistors, then one can manipulate currents on a nanoscale, which say is important for computer technologies, for creating processor chips and creating the electron schemes of nanoelectronics. But we discuss the manifestation of Kondo effect in nanosystems when I will talk to you about quantum dots after your exam. Okay. So, is it clear why it is strongly correlated effect and what it is? So we are discussing not physics of previous century, we are discussing today physics, obviously, which is of extreme interest in nowadays research. If you type in Google Kondo effect, in archive of Google, you will find a number of publications on Kondo effect. So you may see how it is important and how it is interesting, both in strongly correlated community and nanophysics community. Okay. Let's now write down the same Hamiltonian So this is electron density in the position of impurity, and this is impurity spin. And let's ask a complementary question: how two impurities sitting in the position of Ri and Rj talk to each other? So unlike the previous story, where I considered what happens with this Hamiltonian, how it reproduces itself, now I would like to derive effective Hamiltonian describing interaction of two impurities. To do it, I do also perturbation theory. Namely, in order to write the Hamiltonian of interactive impurities, I have to again interact of all possible intermediate states. Which correspond to intermediate states of conduction electrons. So I'm going to get rid of conduction electrons at all. So this integral, this interaction is j over n squared, and I have to take summation of all possible states, d p1, d p2, and p1, 1 minus p2, epsilon p1 minus p2, e to the power I p1 minus p2 minus j, and here it's si for simplicity. What's written here? I have two impurities here and there. This is I and this is Rj. The electrons scatter from this impurity and provide so-called indirect exchange. So in order to use perturbation theory, I have to integrate out all electronic states, which is given by this expression, and as a result, I have Heisenberg-like interaction. You see that this is a scalar product of two spins, but this coupling constant, so I can write it as Ij plus I plus j. And of course, I will need to take summation over all positions of I and j. This is a Heisenberg interaction. But this is my coupling constant Ij, where n are Fermi distribution functions and epsilon is p squared over 2n. I can write down that I R and j is equal to integral over dq iq e to the power I u R and j, where iq is this integral over dp over 2 pi h q and e plus q half 1 minus n e minus q half epsilon e plus q half minus epsilon e minus.
Excuse me. But Ij is not on the Latin sense, it's randomly constant.
It's a very good question. Of course, I have impurities. And because they are put in a random sum. So therefore, I separated. Look, what is written here is precisely iq e to the power iq rg minus 1. So p1 minus 2 is q. So therefore, p1 minus p2. Therefore, I can write p1 as p plus q half, p2 is equal to p minus q half. And this is what I did, and I just defined this iq. Whether spins are sitting in a regular lattice or they are put randomly in the system is known by this exponent. When I take a summation over ij, because I'm not specifying where this. But the q-dependent structure of I is just given by my electron gas. So what I need is to calculate this integral. And this integral is known in many theories. It is so-called Linhart function. As exercise, try to take Fermi distribution functions at zero temperature. Try to take quadratic spectrum of electron gas and calculate this integral. It's not complicated calculation. What is known that this function is a function over times density of states. Here where this function f, I'm not going to derive it. I just write it down. The function f x, so here you see q is divided by twice the Fermi magnitude. Fx is 1/2 1 plus 1 minus x squared over 2x log 1 plus x divided by log 1. This is Linhart function. If time permits, we calculate this function when we discuss the screening of electrons in a Coulomb system, because what is written here is in fact change of spin polarization or change of electron polarization in the electron gas. So this is entirely property of the electron gas. It doesn't know anything about spin system. It just characterizes as electron gas at some temperature. What is remarkable property of this function? For small q means small x. If x is much smaller than 1, then I can expand log in terms of small x. It cancels in the denominator, so this Linhart function is just 1. Plus O over x squared. For large x, however, I need to expand log in terms of inverse x. And one can see that it behaves as 1 over 6 x squared. So if we plot this function, fx 1 x, there is a tail 1 over x squared, and there is deviation from 1 for small x. But you see from here that x is equal to 1, namely when q is equal to kf, is dangerous point, because logarithm is divergent, but it is multiplied by the small value. If you plot the function carefully, the function itself is continuous at x equal to 1. However, there is inflection point with infinite derivative at x equal to 1. Now let's take a Fourier transform of this function in the coordinate to the coordinate space. Again, I denote now x as 2 times kf rij. And rij can still be random. I'm not specifying what rij are, but ix is proportional to cos x over x cubed minus sinus x over x cubed. So this is known as RTKY interaction. And RTKY stands Ruderman Kasuya, Ruderman Kittel, Kasuya, and Yoshida interaction. In fact, this is the indirect exchange, which tells us how the coupling constant behaves as a function of a dimensionless parameter, where 2kf stands for twice Fermi moment of the system. So now your question. Let's plot I as a function of. You see, for large x, I is a function of 2kf rag. For large x, since both cosine and sine are limited by 1, the function behaves as 1 over x cubed on the tail. For small x, one needs to expand. So ix much smaller than 1 is minus 1 minus x squared half over x cubed minus x cubed over 6 over x4. You see that leading term 1 over x cancels out, and what remains x squared over x cubed is 1 over x with the coefficient 1/2 minus x cubed over x4 is also 1 over x. So this is some number divided by x. So this interaction behaves as 1 over x for small x, like Coulomb interaction. It behaves like 1 over x cubed for the tail, and it oscillates as a function over 2kf. Being back to your question. So suppose we now put raj randomly. So sometimes it comes here, then the interaction is negative and impurities interact antiferromagnetically. Sometimes it comes there and impurities interact ferromagnetically. Sometimes it comes close to nodes and they don't interact at all. So you see that in principle one has for this ordered system kind of glassy state where the coupling constant is random itself. Moreover, it can be random both in sign and in value, provided that the angular function has this asymptotic 1 over x cubed and 1 over x.
So it's spin glass.
Yeah, in general it's spin glass, of course. However, you may ask me a question about Kondo lattices, which I already mentioned. So suppose now all magnetic impurities which are characterized by spin are sitting in a regular lattice. The question, how do they interact? Here is the answer. If 2kf of electron gas times the lattice constant in the magnetic lattice is such that the exchange integral is negative, they interact antiferromagnetically. So spins itself interact antiferromagnetically. If it's on that point of the graph, then they interact ferromagnetically. Therefore, in Kondo lattice, the single impurity Kondo effect, which we discussed in the first half of the lecture, competes with the spin-spin interaction. And actually, these competing effects are self-excluding. Because what magnetism wants? Both ferromagnetism and antiferromagnetism wants to align spins in the lattice, to make either ferromagnetic or antiferromagnetic alignment. What Kondo effect likes is to scatter and spin flip. One needs to flip spin, and one wants to flip spin in each and every scattering process. Therefore, if system is frozen or aligned with some spin stiffness, there is no room for spin flip. It means that magnetic order suppresses Kondo effect. On the other hand, the Kondo effect, this spin flip processes, try to screen spin. As I said, the value of spin is screened by its intensity. Screening spin means reducing the Curie temperature, which is proportional to S square correlator. So both effects compete in destructive way. Namely, Kondo effect tries to destruct magnetism, while magnetism tries to destroy Kondo effect. This is another reason for those people who develop theory of heavy thermals to say that this competition between magnetism and Kondo effect leads to very dramatic properties, which on one hand are responsible for strong electron mass normalization, but on the other hand leads to very unusual magnetism and quantum properties. So let me plot two temperatures or two energy scales which we have already learned during today's lecture. So it will be effective temperature related to Fermi energy, and the first plot would be Kondo temperature, which is exponent e to the exponent minus 1 over. Let me say G, where G is J over Fermi energy. So when I have in Kondo effect J over M times density of state at the Fermi energy, which is J over M times M over Fermi energy, this is precisely J over. So this energy scale, as I said, is exponential as a function of coupling constant G. The second energy scale is written here. So it's a J over Fermi energy squared. This is second order perturbation theory, which tells me that the effective interaction between spin is proportional to second order coupling constant, and I don't go beyond. So this energy scale goes quadratically as G squared. So one sees that for small g, square is always bigger than exponent, while for large g, exponent is always bigger. So in this region, the system can be magnetic, say antiferromagnetic, in a Kondo lattice. While in this region, Kondo singlet, this. So actually in a phase diagram, we have some point where the competition between magnetic state and a singlet state, screen state, is so high that we can strongly renormalize both of energy scales, which happens here, and people think that both scales and calculations show that this is true, that for this specific value of coupling constant, both effective magnetic exchange integral and Kondo constant renormalizes to 0, and this is a quantum critical point. Quantum, because the phase transition occurs at 0 temperature, and the phase transition itself is driven by quantum fluctuations. It's not the thermal fluctuations, it's the fluctuations related to Heisenberg uncertainty principle. And one of the messages from that sort of theories is theory of strongly correlated systems where there is a competition between local and non-local magnetism, for example. In many cases result in very unusual quantum criticality, which in turn define this very unusual behavior like Fermi physics. Actually, the same kind of behavior related to indirect exchange. Indirect means through conducting electrons, can also be modeled in quantum dots, and it has been done, and it also leads to very interesting physics and controllability of quantum dot, where spin-spin interaction competes with the Kondo effect and can be used in order to manipulate the spin state with quantum dot devices. Okay, that's probably all for today. What we did was to consider very simple Hamiltonian describing the scattering of conduction electron on local spin impurity, no charge, just spin-spin interaction. And we see that on one hand, these effects lead to strong renormalization of the coupling constant if this exchange is antiferromagnetic, so it can lead to Kondo physics. On another hand, the interaction mediated by conduction electron leads to Heisenberg-like interaction between impurities, which has long-range order and controllable by the density of electrons. We ignore completely spin-spin interaction in the first half of the lecture, just saying that the distance between impurities is so high that we are sitting in this state of the diagram. So it behaves as 1 over x cubed, the exchange integral. Therefore, if we have so dilute system that we are on the tails, our Kondo effect wins. So Kondo impurities are independent, and they first lead to Kondo physics. On the second part of the story, we took opposite limit, namely saying that the concentration of impurities is so high that the first thing which happens is a magnetic order, which is in general spin glass order. So, and when it happens, it prevents system to develop Kondo physics, and therefore this spin glass state is more favorable from the energy point of view. So these two stories, namely this one and that one, are just two sides of the same coin. They're described by the same Hamiltonian, but the physics is very different. One physics is local spin physics, while the second one is non-local physics related to interaction. Okay, questions? If not, we meet tomorrow and discuss other strongly correlated models. Very important role in models and methods.
And one ma với cả ma ma many words.
equation 8, but sorry, equation 8, but question 8, but no. I didn't.